All right, so once again, this is the first week of the school. I'm going to explain how you're going to do the course first, and then we're going to hit some very small portion of the chapter 12. Okay, so here's the thing. I assume you guys all are in group B, right? Part B. Okay, so we are in group B, okay, part B. So this is technically our first in-class meeting this semester. So this is a Friday. And then our next meeting will be next Friday, okay? So we'll be meeting in Fridays here. We have other group, the other group is group A, part A. They all come in class in person on Wednesdays. Over here. So this is how you're gonna do the in-class schedule for each groups. But here's the thing. You guys now wonder, what about Mondays, right? Okay. So here's the thing. In class, if you come to Fridays this semester, today and next Friday and so forth, you actually come in here and have an in-class lecture we're gonna have some chance for extra credit. Okay, so every time you come to the Friday lecture, we'll do a little bit of small activity at the end, and you have a chance to earn certain points of extra credit every Fridays. Okay, here, and then Mondays, you can also come to Monday lecture if you want. There won't be an extra credit chance, but you can still come to Monday lecture. But the thing is, you had to kind of compete with the Group A student as well. But if you want to come and learn organic chemistry in person or real-time setting, if it's better for you, you can definitely try. The good news is we have I think 12 to the 13 students in each group A and B, but the maximum capacity for this room is 18. Okay, meaning even though you can come to this Monday lecture a bit of later time, you still have a lot of open spot on this chair that says X sign. You can still take it, so you can still have in-class lecture on Mondays if you just try somewhat, efforts. Because we only have 12 to 13 students in each pod, so even though they all come, this is also open to the Group A students too. So maybe not all of you, but many of you will have a pretty good chance to attend in-person class Mondays as well. Make sense? Okay. So here's another thing then. So like I said, we only have 12 to 13 students in each pod. We all will come to this in class Fridays this semester. The other Group A, will come to Wednesdays in class this semester. But you can also try to go to Monday lecture. There might be a pretty good chance. And also, think about it. Maximum capacity is 18, but there are only going to be 12 students if they all come to the class. There's still 6 spots open, and also, historically speaking, it is almost impossible that all of students come to the lecture like in every week. So there might be even more spots open on even Wednesdays as well. So if you really, really try, if you want, you can actually come to 3 times in class this semester. Makes sense, right? Okay, so if you want. But if you don't need any extra credits, or you prefer to learn chemistry through the online, like a video watching platform, that's okay too. You're not missing anything, but just a little bit of points of the extra credit. That's it. Okay. So I think if you really want to learn something about organic chemistry, which is not an easy subject, if you prefer to come into the class and kind of interact with me in real time, in person, in the class, you can definitely try more in this semester. Makes sense, right? Do you have any questions? You good? Okay, perfect. So this is something I'm gonna try this semester, but obviously if you come to at least once per week, and every week you have some chance to get some extra credit here. So let me go over the grading scale again for this semester. So I know most of you already took my Olga 1 lecture last semester. So it's very similar to what we did last semester. So it'll be 2 midterm exams. But at this time, this semester, because I don't know if you guys remember, I kind of jumped in the middle of the semester. There's no way I can do it, but at this time it will be a bit easier because each exam will only cover about 4 chapters, not 6. So anyway, this is 100 points for each. So in total, again, 200 points from your 2 midterm exam in this semester. So I have one final exam again. That's 200 points. Okay, this is 200 points. And here's just something I made quite a difference this semester from the last semester. You already have a textbook, right? You guys already have a textbook, right? For you, when you took the Olga 1, you probably have either physical copy or online copy of the textbook. That's the only thing you need to have for this course. You don't have to buy access code or anything. But I'm gonna do Canvas quiz. So we did this for extra credit last semester, but this will be now in one portion of your total grade. So this will be in total 100 points. Here's just something what I'm gonna do this semester, slightly differently from the last semester. I love all online the homework system. It's great, but I wanna try to do the Canvas quiz for your actual homework points because whenever I make the Canvas quiz, when you go over, you know how to take the Canvas quiz by now, right? If you go to home page, once again open up one of the tab menu that says quiz. You just click and it goes into the list of the quiz 1 and 2 and so forth. And so you can solve the problems on the quiz before the deadline, so you can get the full points. And for this one, I want you to remember this one. Whenever you go to do the Canvas quiz this semester, just do not try to get the points, but also try to remember what type of question or what it says on the quiz when you prepare for the exam. So I'm going to make the quiz is very practical for your exam preparations. Makes sense, right? So you definitely have a very good idea what format of the test will be there, and also what question you may see on the exam as well. So in this way, you're actually going to have this might be one of the good study guides for exam 1 and 2, even finals as well. Okay. So whenever you go there, you see lots of the multiple choice questions that you may also see on the exam as well. So just don't try to just get all the points, but also try to understand what it says, what it means, how you get the answer and everything. That will really be helpful for you to prepare for the exams later this semester as well. Okay? Do you think it sounds better? Sounds good? Okay, perfect. So make sure you guys do this. And also, I'm gonna keep the same exam policy for this semester, which is your final exam will replace your lower midterm exam score. So, but this is in the 200-point scale, right? So I'm gonna use the percentile score. So if you got, so this is pretty much the same that we did for the last semester. Maybe you got 50 points for exam 1, but you're having better and better understanding over time. So maybe you got 80 at next time. And then final exam, you got maybe 190. Okay? In this case, you're going to have 95% score for your to replace your lower midterm exam score. So this will be removed. It will be replaced by this one. Okay. So as you already know, this is a really good exam policy. I saw a lot of people did really well on the final exam, and they did really well overall in the course, getting a good grade. Okay. Sounds good, right? You guys already know about this one. I'm just gonna remind you of what we're gonna do again. Pretty much the same thing, same policy for the exam. So, in case of your family emergency or medical conditions or medical excuse, you may not even have to take one of them. Still, can be replaced by your person score of the final exam. So there'll be pretty good way to keep you in a room for doing well in course in the last week of the semester. Okay. Sounds good, right? Do you have any questions about campus quiz or anything? This is the only difference I really made on this semester, but not much else. It's pretty much what we did last semester. Okay. Alrighty. Let's see. Okay. So I'm gonna move on to the first part of the chapter. Is it 12? Chapter 12, I think. Okay. So this is something we're gonna learn about. Do you want me to review certain part over one whenever I do each chapter? Do you guys prefer that way? Okay. Okay. So I'll do my best to remind you of what we did last semester whenever we touch on new topics and the Ogre 2. But the first part of your Ogre 2 chapters are simply quite new because we're gonna learn how to do some measurements for all the property of the chemical compounds. So first one is mass spec geometry. Okay. So this is simply something about this one. So whenever we try to measure some property of the compounds, what we normally do is we try to see some interactions between matter and energy. Okay? So matter simply means what? Obviously the compounds, our organic compounds. Okay, we have some organic compounds. We're gonna treat it with a certain amount of the energy. So traditionally speaking, what we've done for a long time in the back in old even medieval time was combustion reactions. Okay, so you guys remember from Jenkins 1 and 2, some in Ogre 1, that whenever you do some combustion reaction with organic compounds, you're going to have some interaction with the oxygen. They're going to produce a certain amount of carbon dioxide and water. And during this one, you can possibly predict the molecular size and the composition. So how many carbons and hydrogens are there, or how big the molecule is, and how much of the oxygen were involved in these combustion reactions. and you have to analyze each reactants and the products, and then quantify all the reactants and products as well, and to see maybe possibly the size of the compound, and also what this compound is made of, like which element is involved in this type of combustion reaction. So as you can predict, as you can assume, this type of experiment is really time consuming and really complex, because it's really hard to get the all exact amount of the products and reactants can be equally used for 100% reactions. There might be incomplete combustion reaction. You need to think about the air and everything. It gets to a certain point where it can almost can do perfect analysis of the compounds. So we had to come up with a better way to do it. So either we actually do it with a more like a heat energy, right? Combustion is definitely heat energy, right? But at this time, we're gonna use the much more convenient way to interact the compounds with is a light energy, okay? So this is the first part of the Olga 2. Mainly talks about how you're gonna use the light energy. We'll have different types of the light. We're not just talking of the visible light, but infrared and ultraviolet and so on. We're gonna use those type of light to see how this matter interact with them, and see how we can use those information to finalize the structure, sometimes size or composition and so forth in here. The mass spec is the best device, best way to find out the molecular size, how big this is, and also what elements, sometimes not 100%, but compositions, or sometimes possibly structure. It's not always possible, but this is something you can do with the mass spec over here. So mass spectrometry is used for making the measurement of the molecular size, and also some the chemical formula information. And maybe if you're lucky, you'll be able to know, oh, this might be the possible structure you may see from reading the data of the mass spec. But structure-wise, we'll get there sometime soon, but we're gonna learn about the NMR. So we'll get to there sometime later this semester. We'll focus on the chemical formula, possibly, about molecular size. Definitely we can do with the mass spec here. So the name itself, it actually tells you the everything, because this is mean about how you're gonna use the light in here, and how you're gonna quantify the data once you got this all experiment done in your lab and so forth. Okay, does it make sense? Do I speak too fast? It's good. Okay, perfect. So if that is the one, obviously mass spec has a lot of different types, but there's mainly consists of three basic parts. The first one is how you're gonna ionize. So the first part of the mass spec is the ionization. How you're gonna ionize the compounds. And the second part is that they're going to analyze the mass, or the size, you can say, of the compounds. Okay, so this is second part. And then later, you're gonna detect those. Okay. So you're gonna detect those the compounds, and then you're gonna use the data to analyze the molecular size and the chemical formula and so forth. Okay, so like I said, there are certain different types of ionization analysis and detection over here. So the common mechanic you use is a electron impact. Okay, I'm going to tell you more in detail soon, but this is one way. Another way is electro spray, like a spray, like spray. So you electro spray means like making some spray system to make it ionized. And the last one was the matrix assisted laser desorption ionization. So we call this the MADI. This is so we have several ways to ionize the compound. So when you analyze the mass, we mostly commonly use the magnetic force. Okay. Sometimes they use the TOF. It's a time of flight. Okay, so TOF, time of flight, and then sometimes they even use a quadrupole system to analyze the mass of the compound. Now you guys wonder why you mean by mass, because we know the mass is the one, but I will tell you more about the ionization process. You understand why we're having those process later. But those are the three different ways to analyze the mass of the compounds. More precise actually fragment, but anyway. In detector, you're gonna use the either light, so we're gonna be photo multiplier. Okay, and then you can also use electron multiplier. The better version of electron multiplier is the microchannel multiplier. So they're detecting the information by using light. This is why we named it photo multiplier. But obviously you can all use the electron as well. But later we have a better system with the more composite, like a complex electron measurement multiplier, which we call microchannel, because each channel has a very small size. Can also do as an electron detector. So this is the final stage, final process of analyzing your compound with the mass spec, and you're gonna see this on screen. So they're gonna display all the data in a certain graph. So this is how it happens. So once again, sample goes in, your organic compounds goes in. They'll become, first of all, they become vaporized. They're gonna put it in a very nice and high kinetic energy status, which is gas phase. And then they're gonna put a little bit of energy in form of a light. Normally we use the electron beam. I'm gonna tell you more in detail soon. And then what they do is they make those compounds treated with very high energy electrons. They're going to be break apart. So they're going to be some small fragments after ionization. So whenever you go through these three types of either one of the process, they're going to separate those fragments by its size. And then when you all have the detection of each different small fragments of the molecules will be recorded in here, and you're going to see those data at the end. Okay, so but it makes sense that you have three parts for sure, right? Okay, can I move on? So okay, so if that makes sense, I'll show you how is it ionized. So we're gonna use these. So once again, once your sample is vaporized, maybe in a very uniformly disperse in the nice space, and you're gonna put the electron beam. Okay. So this is your organic compound. Okay. And you're gonna put the so when you shoot the like an electron ball. Like you think about you shooting electron to the compounds, then this compound will lose one electron. So this will lose one electron here, meaning you're going to have your organic compounds positively charged, because your organic compound now lost the electron, it becomes positively charged, right? Because you have one less number of electrons than protons now. So you're going to have positively charged, but make sure you guys put this is small dot beside the formal charge plus formal charge, meaning now your compounds become radical. Because if you think about the molecules, when they all make the bonds, it only going to happen in the pairs of electrons, right? So covalent bonds, you're going to share one from each, either one pair, two pair, three pair. It has to be a pair of electron making a bonds. But this electron beam is very high energy, like this is a 70 electron voltage, very big potential difference will hit your compounds with. So they'll make them to lose their electron. So they just don't do anything, but just this electron will be pushed away. So that's why it becomes positive. But now if you think about it, you all had the numbers of the electrons in the compound in even, right? Because they're all pairs. But if you lose just the one electron, it has to be positive, but it has to be radical. You guys remember this? The radical structure, meaning it's very unstable state of the compounds, because now they have odd numbers of electrons. It's not even anymore, because they all have a pair of electrons. That is the one that makes them stable. But because of this high energy electron bombardment, they actually slap them in the face and get the electron away. That's why they become unstable. Makes sense, right? Okay. So if they become unstable, what they do is, because of this high energy electron beam, also the instability of this is what we call cation radical. It's literally what it says. This is cation, but it's in the radical form. So it's cation radical. They become really unstable, and eventually they break apart. When they break apart, for example, I'll give you one example. So here's the thing. If you have a compounds looks like this, right? You have a 2,2-dimethylpropane over here, right? Okay, so if you have this one over here, they'll become positively charged, but radical over here. Okay, so if this happens, they're going to be broken apart, and then they're going to have this. So if you look at the 2,2-dimethyl, the propane over here, you can think this one is kind of one separate groups, and this one another separate group over here, which you can recall from Olga 1. There's top butyl groups, right, in your compound, and so what it does here has to make certain breakage of one of the bonds, and what they do is this one, like this. Okay, so now I all have a pair, but it's the positively charged, but it gets the methyl group of your compounds now broken apart and became separate fragments over here, and the radical form over here. So this is how they break the compounds. And there's one thing I want you to remember is this one. The reason why either they're not doing this one instead is they tend to break the one that makes the cation part of the fragment more stable. So this is also the review, like I said before. Do you guys remember this one? Those are, we call last semester, carbocation. You guys remember this one, right? The carbon with the cation. Which one is more stable? You guys remember this? If it's more substitute with R groups, they're perfect. That will be more stable because of the induction and the hyperconjunction we learned last time. So, but just remember this one, right? So, if that is the case, it is better for this one to carry the positive charge instead of this one, right? So they can be, relatively speaking, they're still quite unstable yet. I mean, they're still unstable, but they can be less unstable in their options they have, right? Okay, so that's why this is the one that carry the positive charge. This is the one that carry the radical electrons. Okay, if that is happening, whenever, makes sense so far, right? So whenever it goes to the, so this is electron. So this sample is vaporized, shoot by the electron beam over here. Okay. I understand this maybe takes quite a time, so I'm gonna repeat maybe even next week too, but don't worry about it. If you have any questions, just let me know. So once it's vaporized, you shoot the electron beam over here, so they can be ionized, even small fragments. So the one with the charge will be accelerated by electrical field because it has now charge, and once it's accelerated in certain speed, they're going to go through the kind of curved pipe of where you can have a magnetic field. Okay? Then think about it. If you have these two, only this one will be curved because this is the one has charge. This one does not, right? Makes sense, right? So that's why they made it curved. So they don't want the one with the radical form. They just go and hit this wall. They're not gonna find it. But the one with the charge will, because of the magnetic force, they're gonna put a certain force of their way they put the electron field on, and then they're gonna do curve. So this is where you can find the detector. So only thing that you find from this electron bombardments on your compound is the one with the positive charge, not this one. Okay, this is something I want you to remember. So this is the reason why they break in this way, and this one will take the positive charge instead of this one. So whenever you look at it on the mass pack, you're only going to see the one with the positive charge, but the one will miss during the experiments. So this will be wasted. Okay, makes sense, right? Okay, good. So just one more thing, very simple thing is if you have a certain magnetic force here to make it curve because it's charged now, but when it's curved, if it's heavier, like when you're driving a truck and you're making like a really like a rapid turn on your driving, it takes more force to the outward because you're heavier. But if you're driving in like a small car, it's easier for you to make a turn because the amount of the force will be smaller. Okay, so they can be more easily controlled. So if it's the heavier, the force will be applied on the charged molecule, but it won't change much of the motion. So we'll actually get to here. It's heavier. But relatively speaking, smaller ones will get the more effects on the magnetic field because it's smaller, weaker, they're lighter. So they'll be curved as it's meant to be in the magnetic field, they're going to the more on this side. So this is how we analyze the mass. Like you saw in the mass analyzer, right? We just try to put it on the magnetic field, then how much it curves based on how heavy that is. So you can see, oh, this is the what fragments, how big fragment that is, or how small the fragment is, and so forth, while you're seeing it on the detector over here. Makes sense, right? So this is the first step, second, and third steps. That's what we talked just before. Makes sense, right? We good? Okay, perfect. So then, if that is the case, I'm actually gonna stop here just with a little bit of example, because I think I need to spend more time. Anyway, so if that is the case, how we can practically use this data for analyzing your compounds. So maybe what you can do is that in this type of detector, whenever you study for the exam, you're always going to have certain type of a graph that I'm going to give you in the quiz on the or in the exam. So the y-axis is for relative abundance. So it's in percentile units because it's relative abundance, and this is the x-axis is the mass per charge ratio. So this is a mass to charge ratio. This is simply, but here's the thing. This is simply the same as the mass, molecular mass, because like I said, when you shoot the electron beam on the compounds, they'll become +1, right? So the mass divided by +1 is always what? The same number you see as a mass, right? Because you divide something by 1 is always the same number, right? 4 divided by 1 is 4, 8 divided by 1 is 4. Anyway, but technically speaking, that's mass to charge ratio anyway. But you can always consider them as same as the molecular weight anyway. Okay, makes sense, right? Okay. So, for example, when we try to do analyze the small organic compounds in the mass spec, maybe use the propane, right? We use the propane. So this is what it looks like. Okay, so you have a certain type of the numbers appear on this graph whenever you do the mass spec on the molecular compounds, and then I can maybe the first thing what you can do is you can try to get the molecular weight for the compounds. You can you know the chemical formula, right? So there will be the 3 carbons will be 12 times 3, okay? And 8, this is simply 1. 1 times 8 is 8, right? So that will be 44, right? 44. That is something you can confirm on the mass spec too, because you see the mass on here. So you're going to see some bar graph, all right, on 44. So now you're for sure making 100% confirmation of the molecular weight of the compound. Oh, that's the one I see over there. It's gotta be the right number right there, which is the right compound. And you have some of the peaks as well, okay? Something like this, because not only for your charged, like positively charged molecular ions. So this is what happens to this one. So when this becomes this one, this is what you see over here. We call this so this peak on the mass spec graph, we call this peak parent peak, because this is what your compounds, the fragments are from. This is like a parent, right? This is the original compound size for your mass spec analysis. So this will be simply the parent peak. This is where you can find the actual molecular weight. That's really great. But you'll see some fragments, like I said, they become unstable. They're gonna break apart in a radical form and charged form. So if you think about this one, will become break apart, right? Okay, like this. Okay, you're going to see this part is coming in. So there'll be 2 carbons, right? 2 carbons, 24, 1, 2. So it'll be 5, right? So 29. So that means you're gonna have a pretty good chance to see the peak right on 29 as well. So you can see, oh, this is for sure maybe propene because 1 methyl group break apart from there. The number you're supposed to see is 29, but you do see the 29. So this is the also another peak you maybe see. And whenever you see the peak that hits the 100% of your relative abundance, this is what we call base peak. Meaning that is the standard for the 100%. And you can see the relative abundance from this base. So this is what we call this base peak when it hits the 100% on the y-axis. And this is the most abundant fragment you may see on the mass spec. Okay? And you have maybe a little bit of other peaks over there, so it's not very abundant there in the fragments combination. Okay, makes sense, right? Okay, so just one more thing. Whenever you call this parent peak, this is obviously this one, right? So we sometimes call this molecular ion, and it goes M positive. This type of symbol. So they're pretty much the same. But another thing I want you to remember is the base pair that is most abundant will be used as 100% standard to get the relative amount of all the fragments or the molecular ions in the data in the mass spec. Okay? Makes sense, right? Okay, good, perfect. So if that is the case, whenever I put those type of bar graph, I'm gonna do just one more thing. I'll finish here. You see a little bit of a tiny peak around like a really long peak over here because of the isotope. You guys remember isotope, right? So it's the same elements, but for maybe carbon, it's 12. But sometimes, in the by very low chance, you also have a carbon 13. So it is very common. You see there's the very small peak around the really like a major big peak on the mass spec because of in the nature, by small chance, you also have some heavier or lighter isotopes than your average value, which is the number you see on the periodic table. So you don't really have to worry about those ones because it's not air, it's just how they are taken in the portion of the nature. So maybe those because of the isotope, it only becomes handy whenever you see the one that has quite a relatively high abundance in the other isotopes like the bromine and chlorine. We're gonna do this in the later lecture. So that's pretty much basic information about the mass spec. We'll do a little bit of a more complicated over next week, and maybe before we move on to next part of the chapter 12. I think it's chapter 12. Is it chapter 12? Anyway. So, all right. Thank you, guys. That's it for today. So,